Okay, so I lied a little bit 2 days ago. I said like we almost finished. We finished with the vector spaces in general. I realized there's one extra little subject which not directly about vector spaces, but a little bit tangential to vector spaces. But I normally discuss that. It's called polynomial interpolation. It's again after we discuss this, you will realize that it all boils down to row echelon form to some extent. So it's a typical question you may see, and which is referred to the area which is called polynomial interpolation. You need to find a polynomial which meets. You need to find a polynomial which meets a particular requirements on values. So polynomial which takes, well, in this case it's a polynomial p which takes value 1 at 3 points, 1, negative 1, 0, 2. And the fourth value at point 1, which is 3. Okay, so that's a typical question which appears in polynomial interpolation. There are a few ways you can solve it. The first indirect way, it's the one which is based on row echelon form. You just basically say, because you're looking for a polynomial of degree 3, you say such polynomial will always have a structure like this with some unknown yet coefficients, and you start going after these coefficients given you have preset values for your polynomial. So you just say, I test my polynomial at the point negative 1 with the unknown coefficients. That's the relation we will see in that case. If I just take negative 1 across this expression, that will be sum of these a's with sign alteration. If I test the value, and on the other hand it must be 1, it's from here. I test the value 0, that's the easiest one to test. I test the value 1, it must be 3, that's a testing of the value 1. And final value I test is the value 2. This is the expression of my polynomial at point 2. This is the value 1, which we must obtain, we must achieve for my polynomial. And this is it. Now you're facing at the system of linear equations with some unknowns. You got 4 unknowns, 4 linear equations, and most likely it will be solvable uniquely. It is in fact solvable uniquely. And we all know how to test that. It's a row echelon form method. It's the first method you have on your hands. So here's my augmented matrix. So for this system, I will extract now augmented matrix. I will take it to the row echelon form, and I will analyze that. It involves some computations. You don't have to do it right now. Like before, I just pre-computed everything on this slide. So this is the this is the augmented matrix of the system we're looking at. If I take it to the row echelon form, in fact on this slide I pre-computed a reduced row echelon form. That's why it's double R. I pre-computed reduced row echelon form. Here it is. And because it's reduced, we basically have the solution straight away, right? Because it's a reduced one, so it has zeros above the pivots. You see, everything here is filled with zeros. You basically just have a solution straight away from it. So my polynomial p is this polynomial. A 3 coefficient from this line is 1. A 2 coefficient from this line is 2. Next coefficient from the next line is 1, and the last one is negative 1. That's the polynomial we were looking for. And that's where the job stops, basically. We have found the polynomial question requested from us. Sometimes you may be asked to find a polynomial of higher degree. So you may be asked to find a polynomial with redundancy. For instance, well, here my p was of degree 3. We found a unique solution. Sometimes questions ask to find a polynomial of higher degree. For instance, if you change the question a little bit, if you just ask for a polynomial of degree 4 this time, and this time I call it Q polynomial, Yeah, this time I call it Q polynomial. It's a 1 degree higher. Imagine we have the same requirements for this Q, even though in the requirements on the slide I use letter P. Let's just say we go for polynomial Q, which also meets the same requirements. So the value of my Q at the points -1, 0, 2 is 1, like in here. The value of my Q at point 1 is 3. I will follow the same steps. Again, I will test my new polynomial at these 4 points. I will see a system of linear equations with unknowns, and I will analyze that system with the row echelon form method. Here's my testing. This is a test for x -1. My unknowns b's with alteration signs right from here. This is a testing at x equal 0, b4 equal 1 from here. This is a testing of point 1. And final test, it's a point 2 test. This test, it's a test. Another system of linear equations with unknowns. It's another, I'm not going to say opportunity, it's another necessity to do row echelon form analysis. You cannot qualify row echelon form as an opportunity. Again, I have pre-computed everything, so this is the augmented matrix of a system. You don't have to copy that, it's a huge matrix, it will take you time for nothing. I will publish the slide, you will see this anyway. What matters actually the result here. So if I take this again to the reduced row echelon form, that's the reduced row echelon form. And again, because we're looking at the reduced row echelon form, the solution is basically we're looking at this solution. However, in this case, because we have more unknowns than equations, we have redundancies. We have we have infinitely many solutions. So in principle, we need to parameterize. So in principle, in fact, we will have plenty of polynomials like Q, which meet these requirements. I will describe all of them with the help of a parameter, of course. And the parameter will be introduced for the non-leading column, which corresponds to the B3 coefficient. So let me just try to describe all of these polynomials which meet this interpolation question of degree higher than of degree 3. So, or in fact, what did I do? Well, in fact, I'm going to parameterize. I'm going to take B3 to be a parameter, but I will choose a parameter rather than like normally we choose T, or canonically we choose T. This time, because you see I have this -1/2 and this 1/2 here, it will be a little bit more convenient if I choose double T. For B3. That will make the expressions for the other coefficients fraction free. So here's the expression for Q. And because you see, because I have not just one but many solutions, I reflected this in the notations. I changed my notation to Q sub T to reflect that we have many polynomials for different T's. We have different polynomials. Here's the expression for Q, which comes from this row echelon form. We can double check this, of course. B4, this is the last coefficient from here. We solve it from this line, and it has just 1 as a solution. B3 is just a parameter, double T, as it is. B2 is this, my solution here, 2 take T. If we double check this, it comes from this line, and it is in fact 2 take T. This 2 take 1/2 of B3, which is T. X3, it comes from, the coefficient next to X3, it's a B1, right? So B1 comes from this line. B1 comes from this line. When we solve for this B1, that's a pivot on B1. You get 1 take 1 of B3. That's why we get 1 take double T. And the B0 solution B naught value, it's the first column, we solve it from here. It's -1 plus t, that's right. Here's my Q. So that's all of the solutions which meet these requirements, which make this interpolation work. You can restructure this a little bit to see the vector space structure in this solution. You can split it like this. You can say, or in fact, one of the observations I will do straight away. If you take t equal 1 here, if you take a particular choice for your t parameter 1, that will vanish this bracket, isn't it? If you take t equal 1, it will be null. So your Q polynomial will drop a degree. It will become polynomial of degree 3, and you will find your first solution, the one we found before, P. That's what is said here. At the P solution, it's a Q1 solution. But if you want to see a linear structure, that's how I say it. You can always make this linear structure explicit in this solution. And here it is, right? You got your Q naught. Q naught is the one which appears if you take t equals 0 across this expression. And then you have this, so you have one vector, and then you have a parameter times another vector. You see, I speak of polynomials as vectors because we're giving this a vector space language spin. Where Q tilde is just those coefficients, that's a Q tilde. Or you can describe it like this. You can say all of the polynomials which solve this interpolation problem, they make a Q naught polynomial, they made of a Q naught polynomial plus elements of this span. That's another way to introduce the vector space language into this problem. Or in fact, that's the best way to look at this problem in the vector space language. These are the elements of a span, right? You just take a vector, you're scaling it. That's how you make up a span of a vector, of single vector. And that's your QT. I don't know, some of you who will continue to study vector spaces or vector analysis further, you will realize that these sort of constructions, when you take a vector space, span as one of the examples of the vector space, if you remember, and you shift this vector space by a fixed vector, these objects, they sometimes called affine spaces. It's a good term to remember for the future. So in fact, the solution to my new interpolation problem in a vector space universe, the solution is affine space. Any questions? Now, any questions? What I would like to address next is this. I mean, both times we just approached these problems, we were lucky to some extent because the row echelon form we had, it was solvable row echelon form. We took it to the the matrices we had, they were solvable. We took them to the row echelon form. We had all of the leading columns, as many as we need of the leading columns, and we were able to produce a solution. As it often happens in mathematics, we're not so much curious about particular solutions. We're more curious of a general rule, why this happens. So in these particular circumstances, the general question will be, is it always true that you will have a solution in such circumstances? Whether we always will have a solution to this interpolation problem, given you have points and the values. Is it true that you can always find a polynomial which meets the requirements to be this sort of requirements? That's a question I would like to address, and that will be more mathematical discussion and vector space kind of discussion. So that will be my next slide, unless anyone has questions in relation to this slide. In fact, this is something which is connected with the tutorial question 104 in the yellow book, and I'll show you the connection. You will see the reason why the slide is titled so this way, van der Molen determinant. So here's my general setting or general statement of polynomial interpolation problem. I have a set of points which I call x, capital X, that's my set of points, endpoints. I have a set of values, P1, P2, Pn. These are the values, these are numbers. See, real numbers. even though actually in this case we can even claim them complex numbers. That's also true. It will be true also for complex numbers. So these are just the numbers. My job is to find polynomial of a preset degree n take 1, such that what happens? Such that my polynomial delivers required values at these preset points. You see my polynomial p I'm looking for at point xj delivers value p sub j, and this one single identity covers all this range of j values. That's a very neat, very effective way to write things. Introducing an index, make an identity in terms of that index, and then specify the range for that index. It's just a way to present things. This is exactly the setting we observed on the slide before. Okay? So the question which I would like to address, why we had a solution back then and whether we're going to have a solution in any other questions like this. Now, in that example we just done, the whole analysis was about the metrics, which is so. I mean, we tried the points, these points across this expression. We ended up with the system of linear equations with the unknowns a0, a1, a2, and all of them up to n take 1. Okay? What I would like to do, I would like to predict this matrix now in its general setting. So I would like to see what sort of coefficients in that matrix we will have. If we've done it twice already on a particular numerical example, I think now we're more or less well equipped to see what happens in the general setting, right? What I'm going to do, I'm going to take these points, and I'm going to put them across this expression. So next to my unknown a0 will be the n take 1 power of x1 in the first instance, in the first try, then x2 in the second try, and then xn in the nth try. Next to my unknown a1, I'll have n take 2 power of either x1 on my first try, x2 on my second try, xn on my nth try, and so on. So what I claim right now is this, that if I write up this system, if I try my polynomial at every of these n points, and I write up this system for these unknowns, a0, a1, an, the matrix will have this structure. Look at the structure. It's a matrix which will be filled as rows with the growing powers of every point in this set. You see, 1, 0 power, x1, first power, x1 squared, second power, next will be x1 cubed, last one will be x1 n take 1, this coefficient. Well, in fact, I just reverse the order. If this is your first unknown, this column must be the first column, but this way, if you reverse the order, if you treat this one as the last unknown, this way, it is the way it is presented in the question 104, actually. So we're going to be looking at the matrix like this, and that's hence the name, actually. The matrix like this is known under this name. I think it's a German. Actually, I'm not sure what nationality of this mathematician, but it's a mathematician who studied this matrix, and since then this matrix bears his name. So it's a matrix which filled with the powers of a preset sequence of numbers. It's a square matrix with a preset sequence of numbers. What I would like to address right now is why this matrix is always solvable. So why it is true that if you take such a matrix to the row echelon form, you will never see an unsolvable result in the row echelon form. And it's a lovely argument. It will take the argument itself is short. It doesn't take much of the writing. I mean, this is the largest thing we're ever going to write in relation to this argument. But the argument itself, logically speaking, it's a difficult one. I think it will take you a while before you fully understand the argument. But it's a nice, beautiful argument. It's a true piece of a mathematics, in fact. It's a rare, true piece of a mathematics you see in this topic. Okay, so we're going to argue, though, not through row echelon forms, but through second method of argument, which you studied in the first semester, through determinants. And it's hence the second word in my title. So let me just introduce a name to this matrix. That's the name I'm going to use. V for the Vandermonde, X for the set which produces this matrix. What I would like to do is this. I would like to compute the determinant of this matrix. I'm not going to take it to the row echelon form. It will be too messy. Maybe. Never try that. Instead, I will try to find the exact value for the determinant of this huge n times n matrix. Okay? The method we have from the first semester of finding determinants is called the row decomposition or column decomposition. Do you remember the method? What does it say? We choose a row or a column, and I'll choose the first row, and then you do this. You take the first element, you cross out the column of that element, you cross out the row of that element, and you multiply by the determinant of the size 1 less. Then you move yourself to the next element, you cross out the column of this element, you cross out the row of this element, and you multiply by the determinant which is left of size 1 less. And you do it for every element of this chosen row. With the sign alterations, this big number you come up with, that's the value of the determinant, right? That's why I have this big cross. So that's what you do. You single out the element. That's how I normally visualize this process from the first semester. You single out the element, the remaining one, that's the coefficient which goes with this element. Then you move your cross. I can give you this cross as a gift, on the printout if you like it so much. Then you take this cross, you move it next, like this. The remaining, so this is the x1 times the remaining elements of your determinant. You do it n times. This is a formula from the first semester. This is the blast from the past. Okay, so I'd like to follow this procedure now, but I'm going to do it in a smart way, not an easy way. I'm not going to write anything actually on the, I'm not going to write any other determinants. Here's my key observation. Listen to this. If I do this process, if I keep dragging my cross across along the first row, here it will be first term, here will be a second term, here will be third term, all of them, the nth term will be here. If I do that, these smaller determinants attached to every position of my cross, those which are underneath, they will no longer have any x1 in it, isn't it? Because x1 will be once in this circle, all of the rest of the matrix which I'm going to use, it's no longer have any x1 presence in there. That's the main thing which I'd like to keep in mind in this computation. It's a good observation. Okay? So once again, if I follow this process from the first semester for this determinant, row decomposition process, first row in this particular case, I use my cross along the first row. Every time I do this subdeterminant, or if I don't know if you remember the name was minor from the first semester. Every time I have a minor, this minor will have elements from x2 and up. x1 is not going to be there. So this observation I'll fix like this. Just move this aside for now. I no longer need this. If I compute the determinant of this matrix of Vandermonde, and if I do row decomposition with the first row, I'll have something like this. First element here with the minor, and this A naught represents exactly that minor. Next element here with the minor, and this A1 represents that minor with the minus though. Next element x2 with a minor, which I just abbreviated with the symbol A2. With these symbols A1, A2, A naught, A1, A2, A, and take 1, I don't know much about them. But what I do know about these symbols is that these symbols depend only on smaller set of x points. symbols aj, for all of the j's, they depend on a smaller set of numbers. That's the main thing I care about in the whole computations. Okay, so let's just move on. This expression we just come up with, it looks like a polynomial, doesn't it? It does look like a polynomial with respect to x1. Plus this, neither of a's depend on x1. So in fact, it is a polynomial in terms of x1. So why can't I just call it? Let's just rename this value a little bit. I call it a polynomial q of value x1. I can do it because we made this observation quite clear. Coefficients there are independent of x1 variable. So it is a polynomial of x1. I would like to factorize this polynomial. You've done quite a few factorizations in the yellow book. I think a few will be in a test, hopefully, if you survive until then. So you're quite proficient with factorization, aren't you? Why can't we factorize this polynomial? It looks scary, it looks abstract, but actually we can easily factorize this polynomial. And here's another observation from the first semester which will be helpful, which will be key to the factorizations. Imagine for a second I'd like to compute value of my q polynomial at point x2. Can I? So if I replace this x1 with x2, this x1 with x2, this x1 with x2, what do you think the value will be? Any ideas? Given this construction we face, well, it looks like a complex construction, but the answer is not so complex as you will see in a moment. What do you think the value of that polynomial will be if I take x2 value in the x1 position? It will be what? The same to what? It will be, yes, but I need a more specific answer, actually. That's right, it will be determinant, yes. Any other ideas? What do you think? Excuse me, hello. What do you think? The gentleman on the far left. Yes, yes, you don't have to turn around, I'm talking to you. Can you still raise your hands, please? Both of you. Thank you. The one on the left, I'm talking to. What do you think the value of this polynomial is? Why? Coefficients are different. Coefficients do not correspond to? Louder, please. To what? Right minus. No, I am worried now. No, keep talking, please. No, let's just think this through, all right? So here goes x2, here goes x2, here goes x2, right? What do you think will happen? Like if I now replace this whole thing with this large matrix, which actually represents this thing, what's going to happen to this matrix? I'm replacing x1 with x2. What's going to happen with the matrix of van der Monde? Any help from there? Yes. No, just wait a second. Your neighbor, please. Yes, you. Why? Lovely, thank you very much. When you plug in x2, that's a key observation from the first semester again. When you plug x2, all of this becomes x2, and you end up with a matrix with two identical rows. For such a matrix, when you compute the determinant, the only value is 0. And that was another key observation of van der Monde. So if I plug my x2 into my polynomial, it will be 0. So x2 will be a solution to that polynomial. In fact, similar argument works with x3, because if I plug x3 into the first row, the first and the third row will be duplicate to each other. If I plug any other value, x3, x4, all the way until xn, I will see the same conclusion. And what do we see from here? My polynomial of degree n take 1, we know all of the roots of that polynomial. When you know the roots of a polynomial, it's not a brain at how to factorize that polynomial. Your polynomial factorizes in this shape. You take the highest coefficient of your polynomial, and then you just write up all of the linear brackets. Unknown, which is x1 in our context, and all of the roots, x2, x3, xn. Isn't that a brilliant idea? I think it is. In fact, well, I told this already. If you ever will be able to come up with something like this on your own, you will make me proud, and actually you will make many people proud. It's a true piece of a mathematics, true piece of the insight and ingenuity. Not everyone is actually capable of these things, including me. Right, let's just focus on this coefficient, the highest one. We still have something in here. The highest coefficient comes, that's the highest coefficient. The highest coefficient is the one which appears if I do this. It's a minor which is attached to the x1, to the n take 1. What can we say about this minor? How can we describe this minor? Huh? What's a minor? You don't have to be sorry. Is anyone in this class know what the minor is? Anyone? Any brave ones? You should know it's the first semester term. I can point a finger into the book, in the yellow book from the first semester where it is defined actually. But let's just be less official. When you do this row decomposition, when you drag this cross across your along a row of your matrix or determinant, this smaller one, that's what you call minor. Minor is associated to this element. When you put your cross here, minor will be the determinant consisting of the remaining rows underneath. That's what the minor is. How would you call it if you explain it to someone, this smaller matrix? You know, now you like the term. You said it pretty well. So. No. How? Like imagine you just explaining something like this, computation of a determinant to your friend next to you, and you don't know the term minor. How would you call this matrix then? Whatever. Matrix defined by all the elements left over and you cross out the one column. Well, now you appreciate the term minor, right? It's only 5 letters to say, and your neighbor will understand you, right? Yeah. Good. So what's about an? Let's just look back at this term, which is a minor associated with this element. So it's a submatrix. Oh, submatrix is a good term, by the way. Submatrix. This submatrix. How can we describe this submatrix or minor? Well, if you look closely at this submatrix, you will realize that's another instance of the van der Monde determinant. It's just size 1 less. That's the one where you no longer have x1 element, and that's the one where you no longer have n take 1. N take 1 power. So this n take 1 is the determinant of the van der Monde matrix of the x1 set, the set which is 1 element less. And that's your case for the mathematical induction. So you factor out all of the linear terms which have x1 in them, and the remaining factor is the determinant of the van der Monde of a size 1 less, where x1 is no longer the case. If you repeat the argument like this for this new set, you will factor out all of the terms where x2 is present, and then you will have another step of the induction, and all the way until the very last one. So the final formula for the determinant, which is very good to remember, looks like this. And that will be the answer to the question 104 in the yellow book. Determinant of the van der Monde, it's the product, this letter, it's like the sigma. You're more or less comfortable with this sort of notations. It means a sum of all the elements when index run from one value to another value. When you see this letter, which is a capital Greek letter pi, when you see this, it's just as good as sum, but this time product of all such brackets for all possible pairs of j and k as long as j less than k. And that's the value for the van der Monde determinant we have just discovered from this beautiful argument of van der Monde. If you look back at the interpolation question, now we see what? We can always solve a question if the determinant, we can always solve a system of linear equations if the determinant is non-zero. In our case, the van der Monde determinant is non-zero when product is non-zero when every factor is non-zero. In this case, it means that if you don't have any duplicates in this set, if you do not repeat the points more than once in this choice of a points, this product will always be non-zero, and thus your interpolation problem will always be solvable. That's the conclusion of the whole analysis here. Yes?
Sorry, I'm a little confused how you found like A and 1 equals the determinant of that line.
Well, this is a mental visual exercise. If you cross this row from this matrix and you cross this row from this matrix, it will be the matrix of the same type where you have only one less element, for which we can use the mathematical induction. You need to spend some time with this, I presume. Any other questions? All right. There's another way to polynomial interpolation. Remember, the subject of today's discussion or meeting is polynomial interpolations, how to find polynomials which meet preset requirements. There's another approach which belongs to the French mathematician now. It's called Lagrange. The French name is Lagrange, and it's based on something which is called Lagrange polynomials. We have 10, 11 minutes to look into that. It's another approach which actually doesn't involve any solving of systems of linear equations, so you may like it. Oh, no, wrong one. But you will see that it's a lot to write actually. So we're facing the same problem. We have a set of points, and we have a set of values. Again, they may be complex. And we need again to produce a polynomial which at given points delivers given values. Before we approach this through system of linear equations method, we just tested the points, we introduced unknown coefficients, and we get a result. Lagrange, on the other hand, come up with a different solution, which doesn't involve any solving of system of linear equations. He just suggested the specially constructed polynomials. You just think of them. We don't know how he did this, but he managed to do that, and since then we just follow his steps. He says, let's just consider for this setting, let's just build n special polynomials. Now we call them the Lagrange polynomials. It will be n different polynomials. I'm going to use the letter L to name these polynomials. There will be n of them. I'm going to use the index at the bottom to index these n polynomials. The index at the top reflects the SAR. It just shows you the degree of these polynomials. It will be this all the time. It will be n. So you can just almost ignore this index. I will have n polynomials. I will index them with the index at the bottom. The top index, it just reflects that this is the polynomials for degree n. Look what he says. He says, let's just take the quotient of this type. It's a long quotient, but there's very simple logic behind this quotient. Look what he does. He says the first polynomial will be the one, and he gave already the factorization of that polynomial. It will be the one which factors into these linear factors, and that's the linear factors which carry all of the points from this set except the first one. First polynomial, we drop the first point. At the bottom, we don't have anything, it's just a number at the bottom, isn't it? There's no any x, which is a variable of my polynomial. There's no any x at the bottom. At the bottom, we just have basically the top where x is replaced with x1. It looks large, but this is just a number. So if you follow the same logic, the second polynomial will be linear brackets at the top where you use all of the points from this set except this second point. And the bottom will be just the top where x is replaced with this second point. That's a second Lagrange polynomial. Again, it's a long writing, but the logic is very simple, and that's what you have to remember. All of the linear brackets with x unknown, with the x variable, except the points x2, and the bottom is where x is replaced with x2. So altogether we have n polynomials like that. The nth Lagrange polynomial, remember I use the sub-index to distinguish my polynomials. All of the points from this set except the last point in the numerator and the denominator where the last point is just plugged into x position everywhere. Very simple logic. What's the beauty of such polynomials? The beauty of such polynomials right here. And I'll just give you this writing using the j index. Every time you plug in such polynomial the point which you excluded, so the same point which the point with the same index as the polynomial, if you plug in L1, point x1, in L2, point x2, in Ln, point xn, every time you do it, so when you plug in Lj, point xj, you will end up with 1. Because remember, the bottom combination is exactly the top combination where x replaced with the point. So bottom cancels the top. That's how we crafted these polynomials. And every time you plug into a polynomial different point, so differently indexed point, you will end up with 0 because one of these brackets will vanish then. Isn't that smart? Every time you plug a point you did not exclude from this long product, you will end up with 0. That's the beauty of Lagrange polynomials. They sort of like filter out the points. The jth polynomial delivers 1 at the jth point and 0 in the rest of the points. It's a very smart construction, in fact. So if I now need a polynomial which delivers these values at these points, all I need to do, I need to take the sum of all of the Lagrange polynomials with the corresponding values. That's another brilliant idea of Lagrange. Why exactly this works? It's not really a difficult argument. In fact, we saw some ideas in other arguments which works here. We don't have time to see the argument. I'll publish the argument. You will check it if you are unable to recover it on your own. In the remaining 5 minutes, instead, I'll show you an example, numerical example. In fact, I'll take this first example today from the first slide when we found a polynomial for a given set of points, and I'll do that example now with the Lagrange method. Any questions? So remember, we had this example. We had this example. We found a polynomial which meets these requirements. We found this is a polynomial. We found this through row echelon form method. I will do the same problem now with the Lagrange. So many things we can do. Here, so my setting is this. This is a set of points from the first example. These are the set of values, P, from the first example. So here's my Lagrange polynomial. I will have 4 polynomials. Remember the logic. I made the linear factors from all of the points excluding this point. And at the bottom, here we go. See? Linear factors which involve all of the points except the first one. X take naught, x take 1, x take 2. At the bottom is the enumerator where x is replaced with -1. -1, -2, -3. This is the first Lagrange polynomial. as with any other Lagrange polynomial, if you test this polynomial at the point -1, it will be 1. If you test this polynomial in any other point, 0, 1, 2, it will be 0. This is a property of Lagrange polynomial. We just discovered on the slide before in a general setting. Second Lagrange, I take all of these points except the second point. I build the linear brackets. Here they are. That's right. And the denominator, I just use the point 0, second point, in the numerator. 1, -1, -2. This polynomial, it's the one which delivers 1 at 0 point and delivers 0 at any other point. -1, 1, 2. In line with the general Lagrange ideas. Two polynomials to go. This is the third polynomial. I use these points except the third point now for the linear factorization here. And then I use the third point in the factorization to make up the denominator. This polynomial makes 1 at point 1, and it makes 0 in the other points, -1, 0, 2. Final Lagrange polynomial. Now I use the first 3 points for the linear factors, and the bottom is the numerator at point 2. 3, 2, 1. The same conditions for my last Lagrange polynomial. If I now want to see the result we saw on the slide 1, all I need to do, I need to combine my Lagrange polynomials with these numbers. Or in fact, it's a linear combination of my vectors L1, L2, L3, L4 with these coefficients. If I do the arithmetic, well, I didn't do the arithmetic on the slide, but I trust you can finish this without my help. If you do the arithmetic, you will see that the result will be the same polynomial as we found on slide 1. A lot shorter than the row echelon form approach, by the way. Especially if you, after a few tries, you will realize how easy it is to construct Lagrange polynomials, not from these large formulas I showed you, no, from the logic behind those formulas. Any questions? Okay, lovely. Now we're done with the vector spaces. Thank you very much. You free to go. Thank you.